Venn diagrams, permutations, and combinations. A Venn diagram is a diagram that is used to help us understand the relationship between sets. So for example, in our first diagram here, we have two circles, and each of those circles represents a set. So we have set A, which would be this circle, and set B, which is the other circle. And a set is simply a collection of things. It could be objects, it could be people, it could be numbers, it could literally be anything. And so if something is inside of this circle here, we would say it belongs to set A. And if it's inside of this circle over here, we would say it belongs to set B. And the overlap that you see in the middle here, anything that is in this region would belong to both sets. And then with three sets, set A, set B, and set C, it's the exact same idea, just a little bit more complicated. So for example, if I were to put something right in this region, we can see that this object would belong to set A, right? Because it's within the circle for set A. And it would also belong to set B because it is within the circle for set B, but it does not belong to set C, right? Because it's outside of that circle. So a Venn diagram is a diagram that really gives us insight into the relationships between sets. Let's talk about unions and intersections. So the union of two sets, which is denoted by the symbol U that you see here, the union is simply all of the elements that are either in set A or in set B. So it's like you're joining the two sets together. Compare that to the intersection of two sets. The symbol for intersection is just an upside down union symbol. And the intersection of two sets is where they intersect. So it is what they have in common. And the intersection can be represented by looking at the overlap between the two sets that you see here in the middle. And from that, we get a definition of what it means for two sets to be disjoint or mutually exclusive. So two sets are called disjoint if their intersection is empty. And in a Venn diagram, what you can see is now set A and set B do not overlap. So there is nothing in the overlap of those two sets. So we call those disjoint sets. A standard deck of playing cards is a really good way to exemplify Venn diagrams and sets. So for example, when you have your playing cards, you will have four suits, right? You will have spades, diamonds, clubs, and hearts. And in each one of those suits, you will have numbered cards from 2 up to 10. And then, of course, we will have face cards, which would be a jack, a queen, or a king, or an ace, right? So we can talk about sets of playing cards within the deck of playing cards. For example, we could talk about the set of spades, right? So the set of spades would be all of the cards that are spades. And so this would be the set of spades. And then we could talk about the set of aces, let's say. Here's all the aces, right? There are 4 aces in a deck of cards. And what I want you to notice is that there is one card that is both an ace and a spade, right? So this would be the intersection of those two sets of things. So one set being the set of spades, the other set being the set of aces, and the ace of spades is in both sets. So we would say that those two sets are not disjoint. They do have something in common. Now let's consider another example. Let's consider the set of spades, right? So here's all of our spades. And the second set will be the set of hearts. And here's all of our hearts. Notice that those two sets are disjoint because they have nothing in common, right? There are no cards that are both a spade and a heart. Okay, so this would be a disjoint set, or these sets would be disjoint, I should say. So in our first example, suppose a sample space is a deck of 52 playing cards. Let the set A be aces, the set B be kings, and use a Venn diagram to show that A and B are mutually exclusive or disjoint. And so you can see that we have the set of aces. There are 4 aces. And then we have the set of kings. And obviously no card is both an ace and a king, which is why there's no overlap between the two sets. So these are clearly disjoint or mutually exclusive sets. In our next example, use a Venn diagram to show the intersection of the set of aces and the set of spades from the sample space. And then we've already talked about this one, but there is one card in both sets, and it is the ace of spades. So here we have the set of spades, which is all the cards that are spades. Here we have the set of aces, which is all the cards that are aces. And the intersection of those two sets is that ace of spades. One more concept that is sometimes useful when discussing sets of numbers is what it means to be a subset. So we say that the set A is a subset of the set B if all of the elements that are in A are also in B, right? So think of it like the set A is inside of the set B. And a really good example of this, just talking about playing cards once again, is you could let the set B be the set of all black cards in a deck, right? And then the set A could be the set of all spades in a deck. And if this is the case, we would say that A is a subset of B, right? Because every spade is also a black card. And again, just to help you see that concept here, we have the set of all the black cards, which would be all of the spades and all of the clubs, right? Those are your black cards. And you can see very clearly that the set of spades is a smaller set made up of the black cards, right? Namely, it's the black cards that are spades. Next, use Venn diagrams to check the following expression. Assume no two sets are disjoint. So we want to prove or show that if you take the set A and you take the intersection with the union of B and C, it's the same as taking the intersection of A and B, the intersection of A and C, and taking the union of those two sets. All right, so first of all, let's work on the left-hand side here. Let's see what that entails here. So B union C is the sets B and C all together. So I'm going to shade in everything that is in set B. So here's everything that is in set B. And I'm going to shade in everything that is in set C. So set C would be additionally all of this stuff, right? Okay, so that blue there, that would be B union C. So now if I want to take set A intersected with B union C, what I'm doing is I'm looking at set A, which is this set, and I'm asking, what does set A have in common with B union C? So if here's set A, you can see that what they have in common, what it has in common with B union C is all the stuff right in here, okay? So this red shading that I'm doing right here would be the set of A intersected with B union C, okay? So here is what that would look like in the end. All right, now let's take the other side, this side here. A intersect B. What is A intersect B? Looking at this part. A intersect B is what A and B have in common. A and B have these elements in common, right? So this is the intersection of A and B. And then the intersection of A and C, right, this one here, would be all of these elements. So this is the intersection of A and C. And then if we take the union of these two sets, right, so if I join all this together, Notice that this is exactly the same thing that we had shaded when we had looked at the left-hand side. So we can prove that these two things are sort of algebraically equivalent by looking at their Venn diagrams. Now, don't worry too much about this example. This is just giving you sort of a sneak peek into set theory, and there's so much more that we could be doing here. But for us, we just need a basic understanding of Venn diagrams. All right, one final example here. Let A and B be two intersecting sets, neither of which is a subset of the other. Use a Venn diagram to illustrate the set of all x's such that, so this dot here a lot of times is a vertical line, and it just means such that x must be an element of A, but it cannot be an element of B. So this symbol just means that the object x belongs to set A and the object x does not belong to set B. And again, don't worry too much about notation here. So what would this set look like? Well, if it has to be in A, it means that it has to be within the circle representing set A. But it cannot be in B, right? And everything that's in here is inside of B. So if it has to be in A, right, it has to be in here, but it cannot be in B. So what we're going to do is shade up to set B, but we're not going to include the overlap between A and B, right? So this right here would be all the elements that are in A but not in B. All right, so now we get to permutations. So a permutation is simply an arrangement of elements or some of the elements of a set. So for example, I could talk about the set of letters A, T, and E. And I can ask you, how many different permutations are there of those three letters? So in other words, how many different orders can you put these letters in? So let's go through them. Obviously, we can do A, T, E. But we could also do A, E, T. So these would be all the possibilities where A is the first letter and then T and E are the next two letters. What else could we do? Well, T could be the first letter, and then we could have A and then E. Or T could be the first letter and then E and then A. And that would be all the different ways we could have the three letters together if T was the first letter. And finally, what if E is the first letter? We could have E-A-T and we could have E-T-A. Now, we've exhausted all possibilities, haven't we? Because we considered what choices do we have for our first letter? Well, it's either A, T, or E. And then once we made that choice, what choices do we have for the remaining two letters? And if you count all of these up, there are 6 total permutations of these three letters. Now, what's really going on here is you have 3 boxes or 3 spots, and you're considering what to put in those 3 spots. And your choices are you can pick a letter to put in each one of these spots. So when I'm choosing my first letter, I can choose any one of the 3 letters. So I have 3 choices. Once I use a letter, let's say, for example, I use the letter A, then for the second box, right, this box here, I only have 2 choices remaining. And then once I use a second letter, I only have 1 choice remaining for the third box. And if we multiply these together, 3 times 2 times 1 is equal to 6. So what if we had more letters? Suppose we take the set of the letters that make up the word English. So we have E-N-G-L-I-S-H. That's 7 different letters. How many different orders can I put those 7 different letters in? So to do this, I'm going to make 7 boxes, and we're going to think about how many choices do we have in each box. So when I choose my first letter, I can choose any one of these 7 letters. So we have 7 choices. Once we make a choice, let's suppose we pick the letter G, for example, For the next box, notice that you only have 6 choices remaining. And let's say for the second box, I picked the letter H. How many do I have left for the next box? Well, I have 5 choices. And every time I use a letter, I have one less choice in the next box. So if we simply multiply all of these numbers together, 7 times 6 times 5 times 4 times 3 times 2 times 1, this will actually be the number 5,040. You can check my math on that if you want. So even just having a set of 7 objects, there are 5,040 different permutations of those 7 letters. So before we give the formal definition of a permutation, we need to talk about a concept called factorials. And in mathematics, factorials are represented by an exclamation point. So if we see something like the number 5 with an exclamation point, the way we read this is 5 factorial. All right. And the definition of 5 factorial is take the number 5 and multiply it by the number that is 1 less than 5, which is 4, and then by 3, and then by 2, and then by 1. And you stop when you get to the number 1. So 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. Now, just to show you how big factorials can get, 9 factorial, which is the multiplication of these numbers here, is 362,880. So factorials get really big really fast. Now, sort of a special case, 1 factorial is defined to be 1. And even a little bit more special, 0 factorial is defined to be 1 as well. Okay, so 0 factorial is not 0. It's equal to 1. And there are reasons for this that I won't get into in this video. So consider the word chemistry, or the letters that make up the word chemistry. There's 9 letters here. How many different permutations can we get of those 9 letters? So we want the number of permutations of 9 different things. So the notation that we're going to use here is P for permutation. We have 9 objects total, and we are selecting all 9 of those objects. So again, we know that for the first letter, we have 9 choices. For the second letter, we have 8 choices. For the third letter, we have 7 choices, etc., all the way down the line. And if you multiply all this out, you get, of course, 9 factorial, which is that number, 362,880. Now let's go ahead and give the formal definition for a permutation. So the formula for the number of possible permutations of k objects from a set of n objects is usually written in pk. Now keep in mind that n has to be greater than or equal to k. All right, so n is the total number of objects in the set. K is the number that you want to take and put in order. So the formula is npk, or the permutation of n objects, taking k of them, is the formula n factorial divided by n minus k factorial. Now, there's a formula here, but I do not recommend using this formula. This can be really confusing. So instead, let me just give you an example. Suppose we have 7 objects, and we want to do a permutation selecting 3 of them. According to the formula, this will be 7 factorial divided by 7 minus 3 factorial. Now, 7 factorial on top is fine. 7 minus 3 is 4. Oops, I wrote that wrong. This should be 7 minus 3, and the factorial should be on the outside. There we go. That's going to be 4 factorial. Now, just think about what factorials are. So 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. And 4 factorial is 4 times 3 times 2 times 1. And see, what ends up happening here is a lot of stuff cancels out. And so in the end, you just get 7 times 6 times 5. And if you multiply these numbers out, you get 210. So what does this mean exactly? Well, if you had 7 objects, but you're only selecting 3 of the objects, for the first box, for the first choice, you have 7 objects to choose from. But once you use one of those objects, you have 6 choices for the next box, and finally 5 choices for the last box. And so you can see it's consistent with what we got here. Now, I personally don't really find the formula for permutations to be very useful. I much prefer to think about it in this way, but this is completely up to you. So in our next example, how many strings of letters can be made from the letters in the word final? So notice that the word final has 5 letters in it, and no letter can be repeated. That is usually the assumption. And in this case, we do need to define what a string means. So a string is going to mean 3 letters in this case. So basically, we have 5 objects, so 5 total. And we are picking 3, right? So we are going to have 3 boxes, if you will. In the first box, we have 5 choices. Once we use a letter, we have 4 choices in the next box. And once we use the next letter, we have 3 choices. So 5 times 4 times 3 is equal to 60. Okay, so there are 60 different permutations of 5 objects, choosing 3 of them. Now, if you prefer to use the permutation formula, this would be 5 objects, picking 3. The formula says this would be 5 factorial divided by 5 minus 3 factorial. This is 5 factorial divided by 2 factorial. 5 factorial is 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. And these cancel out. And notice that you end up with the same thing, 5 times 4 times 3, which is equal to 60. In our next example, in how many ways can 8 people fill 5 chairs at a table? All right. So again, let's assume we have 5 chairs. So we have 5 boxes, if you will, and we will assume that the chairs are in some kind of an order. And we want the 8 people to fill those 5 chairs. So in the first chair, we have 8 choices. In the second chair, we have 7 choices. In the third chair, we have 6 choices. And then 5 choices, and then 4 choices. And we're just going to multiply all these numbers together to get 6,720. And of course, you would get the same thing if you use the formula, 8 objects picking 5. Okay, same thing. And for our final example for permutations, how many ways are there for 3 people from the set of Pat, Diane, Tim, and Joanne to win first, second, and third in a contest? So again, we have first place, we have second place, we have third place. So for first place, it could be any one of the 4 people. Let's say it's Pat, for example. Okay, but we had 4 choices for first place, right? Now for second place, there's only 3 people remaining, so we have 3 choices for second place. Let's say it's Tim. And then for third place, we have 2 choices, right? And 4 times 3 times 2 is equal to 24. Now, of course, you also could have used the permutation formula, 4 objects, picking 3 of them. And you can get the same answer by using the formula. But again, I just think that this is just an easier way to think about it. Now let's talk about combinations. The main difference between combinations and permutations is that in a combination, order doesn't matter. So let's go back to our last example, having 4 people, Pat, Diane, Tim, and Joanne. How many 3-person committees can be formed from these 4 people? So think about this. If we're talking about these people running a race, then if Pat comes in first and Diane comes in second and Tim comes in third, that's different than if Diane comes in first, Pat comes in second, and Tim comes in third. And that's different than Tim coming in first, and then Pat, and then Diane, or Tim, and then Diane, and then Pat, or Pat, and then Tim, and then Diane, and finally, Diane, and then Tim, and then Pat. And I apologize, I kind of did this sort of not very systematically, but if they're running a race, these three people alone have 6 different ways that they can come in first, second, and third. Okay, and that's because when you're running a race, order matters. But if you're forming a committee, in a committee, order doesn't matter. So if we choose Pat, Diane, and Tim, it doesn't matter that we chose Pat first, and then Diane second, and then Tim third. Or if we chose Tim first, and then Diane, and then Pat. Because if you're on the committee, you're on the committee. So with a combination, order doesn't matter. And that means you are going to have fewer total possibilities. So what's the formula for this? So we're going to be looking at taking 4 people and forming a combination, choosing 3 of them. So for the first person, we have 4 choices. For the second person, we have 3 choices. And for the third person, we have 2 choices. And of course, if you multiply these together, you get 24. But then we have to remember that if we choose Pat, Diane, and Tim, for example, it doesn't matter what order we choose these people in. So we have to think about if we had Pat, Diane, and Tim, how many different ways can you make that committee by choosing, Pat first and then Diane and then Tim or some other order? Well, it would be 3 times 2 times 1. Okay, and that means that there's 6 total. So what we have to do is take the total number that we get, which is 24, and we have to divide it by this number 6. And that is going to give us only 4 choices. Okay? So there's a formula for this. The combination formula, which I'm going to show you on the next page, is going to end up being 4 factorial divided by 4 minus 3 factorial. So that's the same as a permutation formula, but then you have to multiply by 3 factorial. And if you do the math on this one, you will end up getting this. And if you cancel out the 3, 2, and 1 there, you get 4. Now, there is sort of an easier way to think about this problem in this particular instance. If you have 4 people and you're creating a committee of 3 of those people, isn't that the same way as saying which person are you going to leave out, right? Like if I pick Pat, Diane, and Tim, basically I left Joanne out. But I didn't have to leave Joanne out. I could have left Tim out, and then the committee would be Pat, Diane, and Joanne, right? So how many different people can you leave out? Well, there are 4 people. So you have 4 choices for who you can leave out. And that would be the total number of committees that you could form with 3 people. So notice that there's another way of thinking about the problem. So the combination formula where you take R objects from a set of N objects, the notation for that is CNR or NCR, or there's this alternative notation here. You can use any one of these, but the formula is N factorial divided by R factorial times N minus R factorial. So as a quick example, how many 4-person committees can be selected from 7 people? So we have 7 things, in this case people, and we are choosing 4 of them. And so the formula is 7 factorial divided by 4 factorial times 7 minus 4 factorial. And this is 7 factorial divided by 4 factorial times 3 factorial, which is 7 times 6 times 5 times 4 times 3 times 2 times 1, divided by 4 times 3 times 2 times 1 times 3 times 2 times 1. Now, calculators do have buttons for these, but we can figure this out without a calculator. 4 times 3 times 2 times 1 is going to cancel out all of these. And then notice that 3 times 2 times 1 is equal to 6. And so I can cancel out the 6 there. And what I have left over is 7 times 5, which is 35. Okay? So we can make 35 different 4-person committees from 7 people. And for our final example, a jar contains 4 coins, a penny, a nickel, a dime, and a quarter. If 2 coins are selected, how many different amounts of money are possible? Well, that's the same as basically just asking how many different ways can you select 2 of these coins. So this will be a combination of 4 objects, choosing 2 of them, which is 4 factorial divided by 2 factorial times 4 minus 2 factorial, which is 4 factorial divided by 2 factorial times 2 factorial, which is 4 times 3 times 2 times 1, divided by 2 times 2. And if you do the math here, you are going to get 6. And that concludes this video lesson.